here and there. Yeah. Okay. First, I just want to know, like, honestly, how do you guys feel about doing the logs and exponential stuff? Like, are you comfortable doing like 1 through 14 without any help? Mickey's like, yeah, cake. I don't need any help with this. How about this to you? Like, I want to know, like, because if you guys are good for it, then I'm gonna skip it and go to the hard stuff. But if you're not, then if you don't know this, then it is the hard stuff. All right, so last chance. If you struggle with solving any of these, let me know. Okay. All right, we started on 25, so I'll do all the evens around 25. I wish. Okay, let's start with 26. So, with these kinds of problems, there are a few mentalities you can go with. My go-to way to do it is, if I can't do it easily without a calculator, my goal is just to convert and immediately do a calculator. Like, if it's something that I can easily convert back, like here, if 5320 was something base 5 that I knew off the top of my head, like, I'd convert to that and then solve directly. But 5820 does not look like one that's going to solve nicely. So instead, I'm just going to immediately convert to a log and try to solve this thing. So do 26. So on 26, we have the following problem. 5 to the 6x power is equal to 8320. To solve this, you remember one of the operations in mathematics is this idea that everything has an opposite, and for exponentials, it's a log. And we want to get rid of this 5 to a power, I have to use a log to the 5. So I'm going to do that to both sides. Log base 5 of 5 to 6x equals log base 5 of 8320. From there, I do a quick solve. Log base 5 of 5 ends up canceling, leaving just 6x. That's why we use a log base 5. If I use a log base 6, it wouldn't work. Equals log base 5 of 8320. And it's like with all algebra problems, my goal is to get a variable by itself, so we divide by 6 on both sides. I end up with x equals log base 5 of 8320 over 6. Now, if I have a calculator, I'm jumping straight to this. I just type it in and get my answer. If I don't, there's a few things I can do. So alternatively, I could use the 1/6 out front, like so, and then move that 1/6 as a power. So again, if I don't have a calculator, this is probably my best bet, and hope that I happen to know the 6th root of 8320. All three of these are the same solution, and almost all of them I'm immediately being like, nope, calculator time, not gonna risk this. Speaking of which, if I don't have a calculator, that's the answer I circle, but if I do, I probably want the decimal version. So does anybody have a calculator with them? Want to type that in for me? What's the decimal? Log base 5 of 8320 divided by 6, or 1/6 log base 5 of 8320, or log base 5 of the 6th root of 8320. All three are the same. So pick your poison, whichever one you want to put in.
It's 0.925.
Beautiful. So again, my goals are standard algebra goals, get the variable by itself, so using algebraic manipulation to do so. And once I've done the algebraic manipulation, I then have the opportunity to see if I can do it by hand. If not, immediately grab a calculator. Don't bother. That's fine. 26. Looking at 28. Same thing. All right. 28. 3 times 5 to the x minus 1 equals 86. All right, let's play a game. JJ, what's my first step? You better believe it. And now it's under 3. After that first step, let's see. Sydney, what would you do next? I would. So log, what base? Y5? The exponent? The base of the exponent? Okay, let's see. Alexis, what next? Okay, Ricky, help me out. Oh, he takes 2 steps. He has to be fancy. And add them one over. And if this is not something I can do nicely, grab a calculator and solve. Make sure you want to do this. Make sure the 1 is not included in the logarithm. Okay? There is my solution, or one version of it. Other solutions could look like log base 5 of 86 minus log base 5 of 3 plus 1. Again, using my formula for logarithmic functions. Any of those works. Without those, let's see. The solution should be like near 3. 2.87. There's my solution. Questions? Want to see how close I am, Ricky? 2.73. That's my guess. So close. Off by 0.3. So we 30. Same concept, same process. Let's see here. First, Alexis, step. Understand where it came from? The base and the exponent always cancel if they're the same. So if it's a base of 5 and a power of 5, they cancel. If it's a base of 3 and a power of 3, they cancel. Base of 10, power of 10, cancel every time. This gives me my variable by itself as opposed to being inside of some function. That's why we use the log in the first place. Okay? Let's try the next one. We'll work through the same process, okay? So something you can look at is you can actually look at a problem from the very beginning and see which base you're going to probably use, whether you're going to use a log or an exponent. Like on 30. 30 says we have parentheses 1 plus 0.10 over 365. So this is a compounding interest formula. This looks like daily compound interest at a 10% rate of t equals 2. So knowing the math here, this is the amount of time it would take to double the formula. That's how the formula looks like. Okay, so if I want to get rid of this function and try to work to get t by itself, my best thing to do is to try to find a log that matches this base. So the base I'm going to use is a log where that's the base. Because no matter what that is, it's going to cancel with this thing because they have matching bases. So 1 plus 0.10 over 365 to 365t equals 2. So by choosing that specific base, I'm going to force these two to always cancel, leaving just 365t. And on the right-hand side, I just make sure do the same thing to both sides. So log of 1 plus 1/10 over 365, 2. So left-hand side, we're left with 365t. Because again, the base and the base cancel. On the right-hand side, we haven't done anything, so it just stays log of that nasty fraction. To get t by itself, I divide, like what we're saying in algebra. Now I'm keeping this nasty thing in the middle of the problem. You could obviously just convert that to a decimal and make it a little easier to write. I'm old school. I will not typically grab a calculator until the very end. So in this case, my solution would be log of 1 plus 0.10 over 365 of 2 all over 365. And then I would grab a calculator from here. That's the only time I would grab a calculator. So again, I use the same base to make it go away. So looking at 25, I would use a log of 3 because it'll get rid of that 3 as a base on the power. For 27, I use a log of 2 to get rid of that 2 as a base of power. For 29, that nasty fraction is going to be my base. For 31, 32, 33, and 34, I'm going to use an exponent of base 2 to match the log, base 10 to match the log, base 3 to match the log, and base 5 to match the log. The only way to get an exponent to disappear is with the log. The only way to get a log to disappear is with an exponent. Question 41 and 32. Let's do 32 then. 32 says log base 10 of t minus 3 equals 2.6. All right. Log base 10 of t minus 3 equals 2.6. 32. Okay. Abby. My first step, please. So, we could use a conversion formula, or we could use an E or a base on each side. It will end up having the same effect. So, you can use conversion. I like that. What's that going to make this become?
10 to 2.6.
So, as a reminder from Algebra 2, there is a formula that allows the direct conversion. You can actually do that on every problem. It's just a simple conversion formula. So for every problem, if you wanted to, you can do it this way. You can also do the log on both sides and the exponent on both sides. It will get the same result eventually. It's just more of a direct step. But it's one you have to remember. So if I was doing this to show it as a different way, and to show that it does in fact give the same solution. So Abby got 10 to 2.6 equals t minus 3. I would use a 10th power on both sides. But when I do that, the log base 10 to 10 are going to go away, leaving just t minus 3. On the left-hand side, 10 to the 2.6, 10 to 2.6. It ends up being the same thing. It's a little faster, but requires you to memorize that formula. Okay, and Casey, my last step to get t by itself. Add a 3 over. So my t would equal 10 to 2.6 plus 3. And again, I'm not grabbing a calculator until right there. Does it bug anybody else that you can't do decimal powers in your head? Like I can do 10 squared, 100, right? But you can't do 10 to the 2.6. Any guesses to what 10 to the 2.6 is? Before you go back there?
400.
400? You think so? Or do you want to go back there?
Yeah.
Alright, what does it got?
401.17.
401. Do what?
I was trying to think of like, how you could do that.
You can't. You can estimate it. You have to be real fancy. So if you know what 10 squared is, it's 100. You know what 10 cubed is, that's 1,000. You can memorize the curvature of 10 to the x power and see that it actually increases over time, which means that even though it's more than halfway there, it's still actually going to be less than halfway between the two. This is how the curvature works. That's one of the actual other uses of calculus. And the biggest really nice. But it's fun. Other functions have the exact opposite effect. Square root functions have that effect. They're always higher. 34? Alright, let's come to you. Ready? So use this one as a framework. Alright, 34. We're going to set it up as log base 5 of the square root of x minus 4 equals 3.2. There is a trick on 34 that if you wanted to, you could employ at the beginning. But you don't actually have to. You could actually treat it exactly the same way we just did 32 and get the same basic solution. Let's try it out. All right, let's just hit me. Log base 5 of the square root of x minus 4 equals 3.2. What would I do first, Alexis?
Use 5 under base equals 5.
Beautiful. That is a great way to approach this problem. It'll cause the log base 5 and the 5 to cancel, leaving just the square root of x minus 4 equals 5 to the 3.2 power. All right, JJ, hit me up, man. What are you next? I've got the square root of x minus 4 equals 5 to the 3.2 power. Yep. So I square both sides. Now, on the right-hand side, if you didn't take the trick at the beginning is where you have to remember a rule. On the right-hand side, so on the left-hand side, we have x minus 4, because squares and square roots cancel. On the right-hand side, powers of powers multiply. This becomes 5 to the 6.4 power. Alternatively, you could leave it as 5 to the 3.2 to the second. And then finally, Sydney, finish me out. Add the 4. So x equals 5 to the 6.4 plus 4. All right, Abby. Looking back at the very beginning, is there an alternative first step we could have taken to make this problem maybe a little different or even a little easier? What do you think? Remember, my original was log base 5 of the square root of x minus 4 equals 3.2. So you're saying to still convert it? That still works. Not going to be a new way though. I'm talking about using a logarithmic rule. So we know we got the answer. We all agree this worked. Is there a different way we could have gotten there, different steps? We know there's got to be some math in there. Any ideas?
Convert it to x minus 4 and 1/2.
Yep. Do it like that. And the 1/2 power can move to the outside using logarithmic rules. So 1/2 would move out front. log base 5 of x minus 4 equals 3.2. And then to get rid of the 1/2, we multiply both sides by 2, thereby getting our 6.4 that we're supposed to get. A different approach. Still works. So you are always allowed to logarithmically simplify first if you wish to, or you could choose not to. Sometimes it's worked both ways. Sometimes one way is distinctly and clearly better. Either way, one of these is going to involve using a rule that's from algebra. But it's either an exponential rule here, or a logarithmic rule there. Either way, you're going to use one. Alright.
Will you do 35?
35? It's just graphing.
No, you have to solve it though, because you have to find isn't it?
It didn't say to solve it.
But
It says use it and approximate its zeros.
on the graph you can't see it.
Oh? Allow me to show you a trick with the graphing utility. If you would be so kind, would you memorize this formula for me? 6 parentheses 2 to the 1 minus 6 minus 25. You got it? Okay. I'm trusting you, Big. Graphing utility. Graphing plane. 6 2 to the 1 minus 6. Okay. Minus 25. Okay. Alright, ready?
Yes.
I'm going to graph. Now, on most graphing calculators, this will not typically graph in the window. So I'm going to have to zoom a little bit and try to see if I can find it. Oh, I actually did. So it appears like there's only one in the window at least. I can go to the table and verify that fact, or zoom out a little bit. If I zoom out, that's the only one. Oh, wait. Yeah, it looks like it's never going to cross again. So I'm guessing there's only one. Okay, well, let me go back to normal. Okay, so how do we estimate that location? Well, if you have a graphing calculator, there's actually a nifty little tool that exists in a graphing calculator. This one. I don't know how many of you guys have taught this in your algebra classes. And in those classes, you might have used the other calculator, which is not as nice in my opinion. There's a feature in here called Calc. It is not standard calculus, it stands for calculate. If I hit the second button on this calculator and go to Calc, it has a bunch of options. Now you notice that some of these are ones we've talked about. It can find a derivative at a point, as long as you can type in the function. It can integrate over a region, as long as you can type in the region. It can also determine a value, so you can determine, hey, what happens at 3? I just type in 3. It can also determine a 0. Now, the 0 is a weird one. Because there can be more than one, a default feature of all of these is that it wants you to tell you which one. If there's only one, what it wants you to do is bound it. So it's saying, okay, left of it is 0. So what I do is I have to pick someplace left of that number. So I want it to go here. I choose a point left of it. I then choose a point to the right of it. And then somewhere in between. It doesn't actually matter where you choose in between. It's trying to make sure that you're only picking 1 0 at a time. Otherwise, it gets confused. Okay? Calculators do not like being confused. This is able to calculate the 0 manually using the calc feature. And this works for any function that can be graphed in the graphing calculator. Again, notice it has some quirks to it. You have to define a boundable range for it to be in and select an estimate as to where that value is. The estimate does not have to be close at all. As long as you're only bounding 1 0, it's going to find it. So again, I'll do that again. I quit. Go back to it. Okay. So to get to that point, I go second and hit the calc command. I want to find a 0, so hit 2, which is a 0. It'll always try to tell me, hey, choose a left bound. So I go to the left of the 0. On the x-axis, I go to the left of it. And I pick a number to the right of it. You can see how it's starting to create a little range in there if you look very closely. And then I get somewhere close to it until, hey, let's look around there. Negative 1.058894. The problem says to go to 3 decimal places. That'd be negative 1.059. That is, I use the graphing calculating feature of this function. And again, this is really nice for the part of the AP exam that has a calculator allowed. Because what if I said, okay, let's find the slope at the point 0.25 or 0.19, whatever it is. All I have to do is go to Calc. I calculate the derivative. And I have to tell it where. You can actually manually find where, or a trick that they don't ever tell you about is you can type in the number. Now, it always will choose the x value. So if I say, hey, what's the slope at negative 1? They'll tell me, hey, the slope at negative 1 is negative 1. If I do the exact same thing and say, hey, what's the slope at 0? I go to Calc. I go to the derivative. What's the slope at 0? The slope at 0 is negative 13. It's very, very convenient if you have a calculator with you. If you want to integrate, same process. Integral has a left and right hand bound. Again, you can either manually find the left hand right hand bounds, or you can type in the left and right hand bounds. I recommend typing every time. Every single time. Always type. Because manually, it takes too long and it's not very accurate. So, the calc command. If you plan on taking the AP exam, I use a TA84 for all my exams. I'm used to it. Whatever calculator you use, if it is a graphing calculator, it has this feature somewhere in it. Somewhere. And if you are taking the AP exam and do not have one of these calculators, you are always looking to borrow one of mine after plenty. So you should bring it back afterwards, or I will have to find you and kill you. You can't borrow my purple one. That is mine. So let's look at the next one to show this problem again, okay? Let's look at 36 this time. Doing a homework problem for you. She's trying to trick me. Let's see how it is. Okay, so 36. 36 says, okay, use the graphing utility to graph the function and approximate its zeros accurate to 3 decimal places. I'm going to use that function. Now, do not forget, if there are versions in T, when you type in the graphing calculator, you can only use the version X. Let's do it. I believe since all these are exponentials and logarithmics, there should only be 1 0, with very few exceptions. So, my function this time was 300, parentheses, 1.0075 to the 12x or 12t, close parentheses, minus 735.41. Never hit enter until you're sure you've typed it in correctly. Otherwise, you may spend 10 minutes trying to figure out what it did wrong. All right. One last thing that some of my students found out during their last exam on the trig test. There is a big difference in the calculator between the negative symbol and the minus symbol. Huge difference. If you put a negative symbol, it will assume you're multiplying by a negative number, not subtracting. That was funny for like 5 minutes. Okay, graph. So, let's see. Oh, this has a loading screen in case you didn't know. The little loading icon is up there. As long as that circle's there, it's still trying to load the graph, so don't freak out yet. Okay, so it's somewhere over there. Perfect. I'm going to zoom out just a little bit so I can see it a little bit better. You can zoom out from the center, which is my most common thing. You can also zoom out from an individual point, which can be very convenient for some things. I recommend getting to know your calculator very well. It seems boring and useless, but let me tell you, I've taken enough exams where I'm like, I don't remember this function, and I'll be like, oh wait, I remember the calculator has it in here somewhere, and I'll go look for it. So please, learn your calculators. All right, if I want to find the 0, I go to second, or shift, calc. I go to the 0 option, which on this calculator is number 2. I have to choose a value to the left of 0 and to the right of that 0. Again, I'm on the x-axis to the left. I usually try to get close. Like this is clearly to the left of it. That is clearly to the right of it. And so in this range, sure. And it tells me that 0 is 10.0000. And so to round in 3 decimal places, that is 10.000. So I would imagine it's actually at 10. Or very, very, very close to it. If it says round to 3 decimal places, then put 3 zeros. It is correct to do so in that case. Because it indicates it is unique out of those 3 decimal places. If this gave me the answer of 10, then all you have to put is 10. There's a difference in scientific notation between 10.000 and 10. Questions? We'll talk about more calculator stuff as we get closer to the AP exam. Like it's useful stuff to know. Stuff that can get you easy points if you don't have to do it well. We got 10 minutes left. Let's do this one. All right, we're here. So for 39 and 40, I'd recommend use a graphic calculator to help you with those. If you haven't graphed the logarithm or exponential function, just use a graphic calculator to help you out with that. For 41 through 62, take a derivative, and that hint I use multiple times when doing these problems. And be very clear in your problem what you're supposed to be doing. So, like for example, on 49, this is 2 to the negative theta times cosine of pi theta. So you're doing a product rule. Usually if I see a log, if there's anything that I can solve on the inside, I want to logarithmically simplify it. Example, 53, that power of 2, simplify it. That square root, simplify it. That division, simplify it. Division, simplify it. Multiplication, simplify it. Radical, simplify it. I would simplify it 3 separate times on number 59 before I even started the problem. Because it will make the problem significantly easier in the long run. It just will. I cannot stress you how much that is true. There's some you can't really get around. 61. There's no good way to get around that one. Because it's not inside the log, that t on the bottom, it's not inside the log, you have to do a quotient rule. We'll practice some of the 42 through 62. Drawing class. Any questions? Are we interested? Okay.